It was early 60s. There were all kinds of wonderful things that have happened in that century preceding 1960s. One of them was very classical, and it's called special and general relativity. So that's beautiful stuff, but it was logical necessity of putting together electromagnetism and gravity, classical subjects, starting with late 17th century. So they would have happened no matter what. It just so happened that some smart people have their name on it, but there would have been an inventor of special and general relativity. There was no choice. And the thinking didn't require much other than saying, well, what happens if light has the same speed in all frames? Special relativity. But then what happens with Newton and gravity? General relativity. General relativity is technically, it requires a clever inventor because you have to be good with lots of tensors. But fundamentally, it's pretty straightforward. I had astrophysics friends who felt it was easier to teach general relativity than special relativity because there is a very nice geometrical picture you can communicate, while special relativity looks a little bit boring, Minkowski metric. On the sidelines of this great excitement of 20th century of making hydrogen bombs and other wonders that physicists did, there were mathematicians. They had to earn their living. Dame Cartwright made her living from military money because she was working on radars. When she discovered strange attractors, nobody paid much attention. But Edward Lorenz was just a weatherman because that's the job a mathematician could get. And he was at this happy juncture. This also had to happen. It was inevitable in the evolution of the species. Once the computers became accessible to people not making weaponry, they had new tool to think. And Lorentz was wondering about whether theoretical physicists would say wondering about turbulence, a very classical problem from 1820s onward, and a problem you could not ignore because we happen to live surrounded by fluids. There is air, there is ocean, there are clouds, there is climate, there is oil that has to be transported from this point to other one. So this is all very inevitable. The only problem was that until access to computers, it was very hard to get any solutions except few relatively boring ones called laminar solutions where the motion is not turbulent. Now, there's no point in claiming that there is a way to do this from Navier-Stokes equation. The main thing is that he discovered that already an interesting to him unpredictable regime, turbulent regime, only happened in 3 dimensions. So this X, Y, Z, they're not coordinates of your classroom, horizontal and vertical Z. They're just 3 physical observables, fields, coefficients of some Fourier expansion of partial differential equation. And what happened is because Navier-Stokes equation has a term called convective term. When you write it out, I will not write it out, but I can tell you in words. It's totally elementary, can be derived in a classroom in a lecture on continuous media. When you transport a little element of fluid, you pick up a term which is velocity times curl of velocity. It just has to do with how the little fluid elements are transported. it's a second order in the field. So equation is not linear, and the remnants of that are these two terms. They're nonlinear. And suddenly, if you had equations in engineering, how to solve differential equation, that typically teaches some boring thing called Laplace transforms. You have tables of them, and they're all linear. Here is a totally elementary first equation you get. You know, they're non-linearities. They are product of 2 out of the 3 fields. And you look at these equations, and it might not be obvious to you, but if you have some experience with these things, first thing you always want to know, is there some symmetry? Because that tends to help make your work much easier if there is a symmetry. So you look at this and you observe that if x goes to minus x, this changes sign, this changes sign. If both x and y go to minus, then this gets minus sign, this gets minus sign, this gets minus sign, that cancels. This gets minus sign, this gets, that cancels. And z doesn't get changed because it's a product of 2 things that have changed sign. So there's a symmetry. That symmetry turns out to be very useful when you really start working. That symmetry says that if I change x and y to minus x minus y, equations don't change. One consequence of equations don't changing their form under this symmetry is that if you have a solution, x of t, remember solving this equation is finding out what happens at time t, z of t. You immediately get solution for minus x of t minus y of t. See? If you put that in your equations of motion, with these 2 guys changed, that satisfies the equations. So if you have 1, you immediately have 2. So you get some saving from symmetry. You know, you have to only compute one of these guys because the other one will be the same. What that means is that if I had a solution, now these are 3-dimensional equation. So let's say I find a periodic solution in 3 dimensions. And let's say it looks something like that. We'll see lots of pictures of them. So a periodic orbit in 3-dimensional state space. Now this says that I can reflect, you know, if this had coordinates z, x, and y, then I can reflect x and y through the origin, or I can rotate the plane by pi. That turns out to be maybe a better way to think. There is a companion solution that has exactly the same shape, just rotated by 180 degrees. So that's what the symmetry means. And then when you think about, actually, there's a special class of solutions in which you look at x of t, y of t, z of t, and they have a property that when I try to reflect them, they reflect into themselves. So the moment there's a symmetry, there are 2 kinds of solutions. The solutions that come as pairs generated by symmetry, and special solutions which self-similar under rotation. And when you look at them in a little more detail, what they look like is they look like x at some different time, because it takes you a while to get from here to there. When you think about it, roughly takes you, I won't write it, but you can figure it out, you know, half of the cycle to get there, and nothing happens to zt because solution is there. So immediately when you have a solution, you classify symmetry, you can classify all solutions as being either not invariant under this or self-dual under the symmetry, meaning they come in pairs. Later on, we'll have symmetries which have not just one copy, but many copies or even infinite many copies. And then you have special guys which are self-dual, and they are all important in their own ways. So that's first thing. It's non-linearities, but you can say something about solutions. The next thing one can think about is volume contraction. And there is a section, very simple section in Strogatz, which you can read, and that's all you need to understand about volume contraction. So what is the volume? You know, in a state space, you can take neighborhood and you'll have some volume of your initial point. And then you can run it for time t. And I showed you already before that the neighborhood will get deformed because it's a nonlinear flow. And you'll get another thing. And the simplest thing you can ask about, you know, I had some neighborhood, it was three-dimensional neighborhood, so I can assign volume to it. Now, if I got time t, is this volume going to be bigger, smaller, same? What will happen to it? So it's an obvious elementary question. And let's do it. If you don't like the way I do it, just read Strogatz section. It uses the divergence theorem, but I will do it slightly differently. So in Chaos book, one of the cheapest per dollar values on the internet, section 4.7 deals with the weighty problem, which is here goes the neighborhood. In mathematics, this is a well-defined, simple problem, and I will discuss it slightly different in the book. The reason is that I want to understand it, not just for Lorentz equations, but in generality of any kind of weather. Here they made an approximation to 3 dimensions. Today, the calculations are in 100,000 or million dimensions because both the programming and the computer have advanced to that level. So I want to keep notion of dimension open. So what's a state space volume? By a neighborhood, a small infinitesimal volume, we mean we have some coordinate system in our state space. So there is an infinitesimal volume, and the picture that we have in mind is that there is a trajectory starting at x0, ending at in some position that's in space-time, time t. And now we're not only interested in point-like transport of a single point in state space, but we assign a little, parallelepiped in d dimensions to initial condition. And we are now curious what this infinitesimal parallelepiped will look like at the end. And the simplest question about it is to say, well, I had a small volume, I call it delta of volume. What is this delta volume going to be time t later? Delta volume time t is, I can write it as a ratio of volume at time t divided by the initial volume multiplied by the initial volume. This ratio for infinitesimal volumes was understood by Jacobi in 19th century. There's a little hypercube for your integral. If you change your coordinates, this is what happens when you move from this neighborhood to this neighborhood. Then you have to compute the Jacobian of the transformation. There are various notations. Here is one notation. It's a volume, so it's determinant of some coordinate transformation from original coordinates to time coordinates at time t times the original volume. This thing, we know what it is. So we have a formula in our terms of our Jacobian matrix. That's why we call it Jacobian matrix, as opposed to very confused textbooks. This is Jacobian matrix. And it depends where we started and how far we went. So this depends on initial point x0 and elapsed time t. And it's a volume. Volumes are positive. So this Jacobian matrix could actually have plus and minus signs because coordinates would actually, go in the opposite direction, etc. after some time. So I have to take an absolute value of it. This is a matrix, and its determinant by definition is product of its eigenvalues. Eigenvalues in my convention, I always use capital lambda. They have an interpretation in dynamical systems, so they're called multipliers. In dynamics, what happens is if I go time t, each eigenvalue has its eigenvector, and the distance along the eigenvector simply gets multiplied by this number. That's what I call multipliers. This ratio of volumes is related to the thing we discussed several times already, especially in last lecture. But the most important thing is that dynamics gives me these multipliers, and we discussed how to compute them. Here comes the second fact that I do not know whether you know or don't, but you must know it sooner or later, so time is now. Whenever you have any matrix, no assumptions of matrix other than it's a finite matrix, and it turns out that I can generalize this even to infinite dimensional matrices, there is a relation satisfied by any matrix saying that logarithm of its determinant equals trace of the logarithm of the matrix. It's very important because it's used all over theoretical physics. It's used in statistical mechanics, stochastic processes, quantum mechanics, and every place. And if you don't know it, learn it. For example, Chaos Book, it's the first problem to do in Chaos Book because it's so important. But, I can motivate it a little bit by saying, suppose I knew how to diagonalize this matrix. In general, stability matrix is not diagonal, but suppose I knew how to do it. So suppose I knew how to write J equals lambda 1, lambda 2, lambda d 0, 0. So I had a diagonal matrix. Then the logarithm of diagonal matrix is defined as this function acting on every element, but it's very easy. This guy is just on diagonal. So I take logarithm of each one of these things. And on the side, I will make a definition. Well, I can write lambda. And suppose even the positive numbers and real numbers, the simplest possible case you can think of it, you can write it at e to little lambda for each one of them. And because this is dynamical systems, for no good reason, I stick in the time, because this was time, and I have, it's multiplicative, so something will be growing like interest rates exponentially. So if I take the logarithm, I will find out that I expect these things to be on the diagonal t lambda 1, t lambda 2, t lambda dimension. Now, I know that determinant of J is the product of its eigenvalues, which I here call multipliers, this big I goes 1 to D. And then log of determinant should be sum of the logs. You know, that's what happens when you multiply numbers, because determinant is a product, so that must be a sum. Logs of these little guys, well, logs of lambda I. And this now is a trace, it's on the diagonal. So this is a trace log of the same matrix. So that's what this equality means. And what's miraculous about it, you don't have to diagonalize matrix. You know, it's true for all matrices. It's a good, nice identity, which we will now use. So now I would like to know what happens to this volume in time. And I have continuous time flow. So the nice thing to do about that is to write an equation for it. Take the logarithm of delta volume at time t. So this is one thing. And how does it change in time? This is the same as computing this determinant times the initial volume, but the initial volume doesn't change in time. So this is the same as computing logarithm of determinant of J at time t from here. But this is the same, you know, it's a logarithm of a number. Determinant is just a number. So this is the same as change ddt of determinant J divided by determinant J. That's just logarithmic derivative. Now this is the same as looking at the change ddt of the trace of logarithm of this matrix. Which is the same trace go outside. This is a matrix. Logarithm of matrix is also a matrix of same dimension. So this is same as d log J at time t time derivative using this miraculous identity. Now, this is the same as derivative of logarithm is derivative whatever it's in here times 1 over Okay, so it's a trace of 1 over matrix J times, now is inverse defined? It's defined because we're assuming that this is a non-zero. Our volume doesn't get scrunched to 0, just smoothly changes. So inverse exists. So now I'm looking at d dt of this matrix. Now remember that last time we defined that derivative of a matrix equals the stability matrix times the matrix itself. There was an equation that enabled us to compute the stability finite time by integrating this relation given the velocity gradient or stability matrix. This is stability matrix. Which you remember looked like a IJ was the velocity in the original equation, gradient with respect direction J. So that means that 1J over derivative is just a trace of my stability matrix evaluated at time t. But this is matrix of velocity gradients, so that's the same as d goes to infinity. The gradient of ith gradient of the width component. And, this you might recognize as a divergence of the velocity, if you like that notation. So now we have a relation between the divergence at time t, and remember, we are moving on a trajectory. So time t means wherever I ended up by solving my equation, motion at time t, it's evaluated at state space position at time t. And that's the rate of change of logarithm of local infinitesimal volume, or logarithm of determinant of my thing. So that means that I can now integrate both sides to get rid of this. So I can integrate 0 to t delta tau. On this side, well, on this side, I'm integrating the derivative of the function log that, okay? That means I evaluate J, log that J, sorry, that's very small, I agree. At time t minus logarithm determinant at time 0, no change. And then I remember J is something that tells me how the volume changes. So at the initial time, I initialize it to 1. because nothing changes at 0 time. So this is 1, logarithm is 0. So this integral equals logarithm determinant of jt. That's integrating this side, but I cannot integrate the other side. So this equals 0 to t d tau delta, divergence of t. But I also remember that this is a matrix. I can find the eigenvalues at instant t. So this is a product of its little eigenvalues. L at, well, sorry, I. Now, on left-hand side, I have a logarithm, and on right-hand side, I have this thing. So I have a solution for my volume at any time by exponentiating this side and this side. So I get the formula that says my local Jacobian at time t. So that's telling me, how the volume has changed at time t equals e to the right-hand side, which is an integral of tau going from initial point to final point of v of tau delta I, divergence of it. In other words, I'm moving on a trajectory starting at x0 to x at t, and I'm supposed to evaluate this quantity, which I know, I have it. It's given to me, so I can compute it numerically if I want to, every place along this trajectory. And its integral will be the change of the volume. So this I know. And it's easier to compute, especially for Lorentz. It's kind of trivial to compute, as I'll see, but I want to look at the very general case for everything. This matrix, AX, the matrix of velocity gradients, is something. So velocities, if there are no singularities, they don't go to infinity. And similarly, if there are no singularity, this matrix is bounded from above. These elements here, they have to be smaller than some number. Doesn't matter which number, but main thing, it's a finite number where m is just some constant, and you can do it better or worse, but that's all it is. Constant number. So that means that this zero to the t trace of this quantity, which is a subset of values, d tau delta I vi, and now I use convention whenever I have same index, I sum up over it, so I don't have to write the sums all the time. Around time, this is always smaller than 0 to t delta tau. Just a number m, which means that this thing is bounded by m times t. So this quantity doesn't grow faster than linear in time unless you have a very sick theory where things explode, but our flows are never that sick. If it happens for Navier-Stokes and you can show it, you get $1 million. But we don't believe that will happen. So that means that what you really want to do is you want to compute an average. This thing at most is going like time. So let's look at an average in time. I'll use this to mean time average. That's what this overbar means, which is defined as limit of t goes to infinity. And you're allowed to do this because this number, 1 over t, never goes faster than time. So you can compute this delta I vi of tau computed on my trajectory, integrated, of course, delta tau from 0 to t. It's just this integral, but because it doesn't go faster than t, the average is well defined, it's bounded. It could be 0, but in the example we'll look at it right now, it'll be a constant, so it'll be good. Now we have another expression for this time average. The gradient of v is summed over I is a trace of a velocity gradients matrix. And now the convention, whenever its index is repeated, I don't tend to write it, but here, just to be boring, I will write it for once. I equals 1 to dimension. When I go back to my formula, I find that determinant of my finite time Jacobian, and that's why last time I was being so insistent in finite time Jacobians versus instantaneous shear of the neighborhood, which is given by this matrix A. This trace, by our definition, determinant of this, and to make it sure we don't get signs wrong, absolute value of determinant, that was the ratio of the infinitesimal volumes, or what's usually called Jacobian. This is E, but I remember that I had a relation between multiplier of the flow and its exponential form. Absolute value was T mu I. That was just definition how to go from logarithms to exponents. And now you can see why I introduced this T here, because it will cancel out. This is a product. Determinant is a product of absolute values of multipliers in different direction. I equals 1 to the D. And by this definition, this is E to the sum of T. Product becomes sum and exponent. This T that I introduced here to make this number a rate per unit time cancels with this T. And we get a relationship that says that the determinant of j of t is e to the average, time average of the divergence or e to the integral t trace of this matrix A. So this is an example of relating finite time change of dynamical system, the simplest one, to the integral over instantaneous shear along the orbit. But now we have another expression for it, which says it is equal to the e to the t sum over the rates of change and these guys in eigendirections of this matrix, finite matrix. And these guys have a name that you must have seen, and we mentioned it before. They're called Lyapunov exponents. They have a property that if lambda I is smaller than 1, means we are shrinking, that will imply that this exponent here will be negative, and that will be called contraction. That means that the state space volume in that direction gets smaller and smaller as the time you go. If they are larger than 1, then we have expansion. These guys are positive, and things expand. If you do what I last time said you can do, if you solve this equation numerically, this one, you can think of it, this has bounded size coefficients. So if you solve something whose derivative is proportional to itself, you'll get an exponential, which means that you'll get things that will expand exponentially with time, which means that as you try to go to higher times, you will lose digits of accuracy, and pretty soon you'll lose everything. No computer will be able to go beyond some time. So that's a nice formula to write, but it's useless. And also, if A happens to be negative as a coefficient, then it means that corresponding value of J will be exponentially decreasing. So you'll be losing digits of accuracy until you'll get to 0 in finite time, and you'll be able to predict nothing. However, because we have a relation that says, basically, if you have solution up here, where the answer is proportional to a number that's bounded times t, this number you can compute because this is a bounded number. So it turns out that you can beat the exponential growth by using the relation between logarithms of determinant to traces of logarithms, which now relates everything to quantity that's proportional to time. So if you take a logarithm divided by time, you get a quantity that approaches a constant. And you can do your calculation. Now you have a result that says the time average is something that's computable. This I have, formula for this I have because I have formula for velocities and their derivatives. This is bounded. I can divide something that grows linearly with time, by t, and I won't lose accuracy like I would do by exponentials. So this is eminently computable thing. And you're happy, you go home, you say, that's fine. But here comes excitement. Let me just do it first for Lorentz to see that it makes sense. What happens to Lorentz equation? Here it is. So I can compute this matrix. I even did it before. Aij is 3 by 3 matrix. I take derivative of first time with respect to x, I get minus sigma. With respect to y, I get sigma. No dependence on z, so I get 0. If I take derivatives with respect to y, I get minus 1. Second term, I get r. Third term, with respect to z, I get x. And if I take derivative with respect to z, I just get minus b here, 0, 0. So the trace of this thing is the sum of the 3 terms on diagonal. And this was 1, so I made an error. When I take derivative with respect to x, I get r here. So I get plus r minus 1 plus x. So trace is miraculous. He was lucky. Usually doesn't happen. Sum of these 3 terms is minus 1 minus b minus sigma. And we didn't tell you this, but in the examples we're interested in, these guys are positive. So this is a negative number. So this integral I'm supposed to compute here, this one, that tells me that determinant of j at time t is e to the 3 numbers, t1 plus b plus sigma minus t. So the Lorentz example is, very trivial. The volume grows exponentially. Now, what does that mean? It means that the volume has to be smaller than the dimension of the space. Dimension of the space is 3. And most naive thing, you would say, well, this just shrinks, so it goes to 0, volume goes to 0. So dimension of the attractor should be 0, meaning I just go to the point. This is true for some parameter values that we'll discuss for this guy. But now the miracle happens, and that's why it was very helpful that Lorentz was a student of Birkhoff, the great mathematician whose specialty was chaos, what we call chaos. Professionals call rigoric theory. From determinant of 3-dimensional volume going smaller, going to 0, only thing you can conclude is that attractor dimension is smaller than 3. So it turns out that dimension, and we'll explain this, it's called a fractal dimension of where you end up. For example, if you end up on a limit cycle that has dimension 1, so that's a possibility. You end up either on a fixed point, which is 0, you end up on a cycle, which is 0. But it turns out that when chaos happens, dimension is larger than 2 dimensions. If I remember correctly, we have it to lots of digits as 2.06, slightly larger than being a plane, but it's smaller than 3. So that's the first exciting thing about this result. Now, here is why I got excited today preparing the lecture. You know, what happens if you're not in 1890s, but you're interested in what's happening in the seminar given at one of the leading nonlinear science institutions in the universe, Georgia Tech, and you discuss a turbulent attractor, so Navier-Stokes or its relatives. So then what happens is that the sum here doesn't go to 3 dimensions because there are not only 3 Lyapunov exponents, it actually goes to infinity. And how is that okay? Well, what happens is that I told you there are 2 kinds of values for the multipliers. Either they expand, now that's trouble. So you have to control those things because things can explode. So it turns out in examples in fluid dynamics, and Lorentz is the first example, there is one positive expanding direction. We'll figure out for length. There happens to be one marginal direction motion along the circle for which mu is exactly 0. So that doesn't contribute anything interesting to the sum. And then turns out there is one negative value. There's a direction in which you contract. And no problem. But in fluids, there are more and more and more of these guys. So when you look at this determinant, there will be some unstable direction, expanding ones, and then there'll be contracting ones, which are not much smaller than 0. But then if you start with a fluid and you start with initial condition which has very wild fluctuations of velocity field, viscous fluids don't like this. So if you start in a kinky solution, so you hit it with a hammer, your piece of water, these guys will immediately get wiped out by viscosity and get smooth, meaning that they will have large negative exponents along directions. And now if I look at the sum, it's going to be dominated by large negative numbers. So you'll find that the determinant of the volume of a fluid, which is computed in infinitely many dimensions or on computer in 100 or 1,000 dimensions, is some huge negative number times t, which means that for all practical purposes, this is 0. So that looks like not very useful formula. What do you get out of this? When you look at these exponents, the local shrinking and stretching rates, you can order them. So you can write mu of I by writing the positive guy first. So there is direction, most unstable direction, the next most unstable direction. Then there is always this marginal direction. If you don't believe me, you can ignore it. But then there is mu of, that happens at some value, so I don't know, n plus 1, the next guy. This one is negative, so these ones are all positive, so they're expanding. This one is negative. And there are infinitely many of those contracting. And when you think about it, you don't care about these very negative things. So for example, if you take, a cup, a tasteful cup from Danish royal porcelain, and you shake it at human velocity irregularly, there'll be some turbulent motion of the tea in the cup, but there will be no kinky stuff on, wavelengths of angstroms or even millimeter. It'll be rather smooth because of viscosity. So you don't need all these guys. So what do you actually need? What you need is a truncation of your sum. So don't use all exponents I equals 1 to infinity, that's boring. That cannot be good. Don't use too few exponents, because if you just keep the first one, the thing will blow up, but that's not what you see. Your volume doesn't blow up. So keep enough of them, called dimension physical, such that if you had the one less, the thing would blow up because the positive guys would dominate. But if you have one more, you would find out that the volume contracts, but kind of nicely and slowly. And if you add more of these contracting dimensions, they just get wiped out by viscosity. So the dimension of the attracting set is such that if I added a mu of d plus d physical, this would contract too fast. And you come to an amazing conclusion, which is hard to understand. You'll see why, because you have to get used to the idea that dimensions are not integers in nonlinear dynamics. They can be numbers which are non-integer numbers, so-called fractal dimensions. But you find out that to describe turbulence in infinite dimensional systems, you only need a finite number of dimensions. And even though your equations say there is 1,000,000 dimensions, you might find out that the correct number is only 6 or 7. So what happened to Lorentz in his limit, it was actually good to assume the dimension is 3, even though he was looking at a fluid, because all the other motions that people added in their truncations on Navier-Stokes turn out to wipe themselves out by viscosity very quickly. And that the physics actually happens on an object which we will study here, called strange attractor. And in fluid dynamics, it has a really weird name. I apologize, but I didn't invent it. It's called inertial manifold. Mathematicians love word manifold. It says the space is not flat, but it's curved. So there's some kind of curved blob in 1,000,000 dimensions, which is actually only 7-dimensional thing, much smaller. It's bigger than a point, but it's a finite number. And inertial is a stupid word that had to do with the fact that nonlinearity of fluid dynamics has to do with inertia of little pieces of fluid. So I apologize for that. Just looking at this simple formula that relates the volume in phase space to instantaneous shrinking and shearing of the neighborhood described by the matrix of velocity gradient, led us to a very deep physical result, saying that we can actually study dynamics in infinite many degrees of freedom if they are contracting, meaning negative. And we can, we only have to keep few of them. Now, this kind of argument you might find very hard to believe. I found it very hard to believe, but we have verified it, with more and more practical utility in recent years, because we can compute and we can find these things. And that's very nice. It says that what I'm teaching you here, which is, clocks, biological clocks in 2 dimensions, and I'm reaching a weird model of matter in 3 dimensions, this actually telescope itself to the problems that we really care about, which are systems of large complexity of many degrees of freedom. In in engineering, they might be called turbulence. In neuroscience, they might be called brains. But you find out that the important dynamics, things that you have to understand, happens at much smaller dimensions than what you would naively think. Last minute of this lecture, there is another situation which symmetries might lead to if the divergence mu v mu summed over all directions mu, if this is 0, the flow is called incompressible. Familiar example is three-dimensional flow of water, which unlike air, you can assume it has very high Young modulus, so you can assume that it's incompressible. It's a very good description. And when the flow is incompressible, that means that at all times, the determinant of your J, T, is 1. So volume of the neighborhood doesn't change. And beyond obvious picture of fluids, it turns out that all Hamiltonian systems have this property. So there's a huge range of applications of nonlinear dynamics. Volume doesn't compress, and that's volume in okay. So that's it for now, and next time I'll exemplify this just by going into Lorentz in more detail. But the big idea, amazing idea, is that you learn this silly stuff in 1, 2, 3 dimensions, and these concepts are applicable in infinitely many dimensions for problems that we really care about, starting with Lorentz, who couldn't do it. We can now do them in the third millennium, and that's what your research might be, because you will be doing third millennium research. Okay. I'll go back to not being excited and just teach you Strogatz again. This is not in Strogatz.